Welcome back to Arxflix. Today, we're exploring a groundbreaking paper titled FP8 LLM, Training FP8 Large Language Models. This research tackles the challenge of efficiently training large language models, LLMs, by leveraging the power of FP8, a low-precision data format. Training LLMs is notoriously expensive, with models like PaLM and GPT-3 requiring massive computational resources. This paper presents a novel FP8 mixed precision framework that significantly reduces training costs without compromising accuracy. The paper highlights the limitations of traditional training approaches using FP30 or FP16 BF16 mixed precision. FP8, with its potential for 2x speedup and 50 to 75% memory and communication savings, emerges as a promising solution for scaling next-generation LLMs. This figure illustrates the potential of FP8 for training larger models compared to BF60 on a cluster of NVIDIA H10 GPUs. The paper introduces a three-level FP8 mixed precision framework that gradually incorporates FP8 for gradients, optimizer states, and distributed training. The framework addresses challenges like data underflow and overflow, and quantization errors inherent in FP8 through two key techniques: precision decoupling and automatic scaling. Precision decoupling assigns reduced precision to components that are not precision-sensitive, while automatic scaling dynamically adjusts tensor scaling factors to prevent underflow and overflow during communication. The paper evaluates the FP8 framework on GPT-style models, demonstrating significant benefits in terms of memory usage, communication overhead, and training speed. This figure shows the training loss curves for GPT models of different sizes, trained with both FP8 and BF16. The results indicate that FP8 achieves equivalent performance to BF16. The paper also reports comparable performance on various downstream tasks, including instruction tuning and reinforcement learning with human feedback, RLHF. The paper proposes an automatic scaling technique to address underflow and overflow issues during FP8 gradient-all-reduced communication. This equation represents the automatic scaling technique, where Gi is the gradient on the ith GPU and mu is the auto-scaling factor. The paper also introduces a mechanism to scale FP8 gradients across GPUs using a single shared scaler, reducing communication overhead. The paper explores the use of FP8 for the optimizer, specifically focusing on Atom and its variants. Through precision decoupling, the paper identifies that gradient statistics can tolerate lower precision, while master weights require high precision. This equation represents the memory consumption of the Atom optimizer using FP30 for all variables. This equation represents the memory consumption of the FP8 optimizer, significantly reducing memory footprint. The paper extends FP8 support to distributed parallel training strategies like tensor parallelism and sequence parallelism. This figure illustrates the integration of FP8 into tensor and sequence parallelism, highlighting the use of FP8 for activation communication. The paper also proposes a new FP8 distribution scheme for zero, distributing tensors as a whole across devices to avoid partitioning and scaling factor complexities. The paper concludes that the FP8 mixed precision framework offers significant benefits for training LLMs, including reduced communication overhead, memory utilization, and training time. The research paves the way for future exploration of FP8 and potentially even lower precision training for LLMs. Thanks for watching Arxflix. Don't forget to like, subscribe, and share this video with your fellow researchers. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.